It's not about the board, but can I use the bathroom?
Yeah, of course. I knew the answer to that one. Amy. 26. Okay. So here we're just asked to do a composition. We're asked to do it both ways. So f composed g of x, I know is f of g of x. In this problem, g of x is 1 over x. So when I plug 1 over x in for x, I get that. And 1 over x squared, we square the top and we square the bottom. So that'll do. Is that okay? So I plugged in 1 over x into the x for my f of x.
Okay.
Is that okay?
Yeah.
Okay. And then it also wants us to do g compose f of x. So that's g of f of x. In this problem, our f of x is x squared minus 3. And so I'm going to plug that into g of x. So I just end up with 1 over x squared minus 3. Right? Because I'm just plugging this then into my g of x. Notice those look kind of similar, but they're definitely different, right? One of them, the minus 3 is in the numerator, or is in the denominator, and the other one, the minus 3, is like its own separate fraction. Oh, Alonzo, what's your first name again? Loretta. Goodness gracious. You can tell it's the end of the day.
Number 29.
Okay. So 29, we're asked to find two functions, f and g, whose composition gives us this third function. So answers here may vary. There's several obvious answers. Typically, when I try to do a problem like this, I'm involving composition. I'm going to look for like an outer function and an inner function. So if I'm plugging, this is f composed g. So f would be my outer, and g would be my inner. So like that's probably the most obvious answer. Does that feel okay? What else could we have done? Well, you could have done this, which is probably a little less obvious, but also would work. Right, where I'm going to plug x squared in for x, and that'll give me the desired result. Or the ultimate cheat code is I can just make one of the functions h of x and the other function x. For composition, y equals x kind of acts as the identity function. So like I can do that with anything and it'll just give me the same thing back, right? If I plug sine of x squared minus 1 into x, you just get sine x squared minus 1. So you can do that. That's kind of the cheaty way of doing it. But like those are probably the three that come to mind right off the top of my head that would be reasonable answers. There's probably still more that you could have come up with that would be okay, but it would have involved like some stuff canceling out or whatever that would have been a little less obvious. Lexi?
I had trouble determining whether 32 was a one-to-one function.
Okay. So all we need to do to check if it's one-to-one is just look at the y coordinates. Are any of them repeated? One-to-one. Here's the thing though, when you say if it's a one-to-one function, it's not a function.
Yeah,
right? It's this is a one-to-one relation, right? It's not a function because we have the repeated x coordinates, but a relation can still be one-to-one. Of course. Is that cool? Lexi, you're good? And that's just kind of, if we have a set of ordered pairs, that's all we really need to look for is repeated y's for one-to-one. You got another one?
Yes. Also, what do you want us to do for the graphing portion?
When you would...
Like 39.
Oh, 39.
Like, I can't really see the...
Oh, so you can't read that well enough to tell what the numbers are? You know what? Like, just kind of estimate it as best you can. Like,
That's what I did.
you can assume every tick mark is 1 unit and just do the best you can with it. Like, I've made a note that I have to go back and like adjust some of these images here because clearly this wasn't very doable. When I embedded these in here, I thought I would get better resolution than I did. They looked good on the screen, and then I got the PDF and I looked at what you guys have. I'm like, ugh. Oh, okay. So again, if those are kind of spotty, it's not the end of the world there. Amy. 27, that's the same idea as 26, right?
Or sorry, not 27, 28.
Oh, 28. Oh, okay. So did you do 26? Oh, we did 26. Got it, okay. So 28 is asking us for F compose G of, was it 3? Negative 3, okay. So one thing I could do, well, I know what F compose G is, right? We already answered it here. So I can just like plug negative 3 in.
28 wants
Oh, well, okay. So then it's this one. So you could do it that way since we already know what the composition is. If you didn't want to have to do the composition, the other way you could do this is you could do G of F of negative 3. So F of negative 3 is going to be negative 3 squared minus 3. So that was just 6. And then G of 6 is 1 over 6. That way, if you do it that way, you don't have to have done the composition first. So depending on like what you've done in this problem, since we already did the composition in 26, it's easy to just plug it into our answer for 26. If it was, I hadn't done the composition yet, and you're like, ugh, this looks like it's going to be a terrible composition, you can do it that way and just plug it into the inner, take your answer, then plug that answer into the outer. And that's okay too. Does that feel okay, Amy? You're welcome. So depending on what you've done, one of those two routes may be easier than the other, but they'll both get you to the right answer. Anybody else? Coolsville, daddy-os. Let's get after section 8 then, huh? So section 8 is about graphical transformations. So the big idea here is that we can create these families of functions, that are based on some parent function, like y equals f of x, and then we do some kind of transformation to it, and we get this new version of f of x called the resultant function. So we'll do some operations to our f of x and end up with this new resultant function. So we'll talk, this is the main idea of what we're going to be talking about today. What I want to start with, though, is some recall from our geometry class about the types of transformations. So this was something that you would have talked about in your geometry class, and I know that was a long time ago, but there were 4 types of transformations. Does anybody remember any one of those 4 types? Drake?
There was I don't remember the correct term. So
that's okay.
Scaling.
Great. So hold on, let's do them one at a time. So like he says scaling. The geometry term there was a dilation, where the graph is like stretched in some way. We're just going to call that stretches and shrinks. And there is 2 types. There's a horizontal stretch or shrink. And the way we transform our f of x is by multiplying the x value by some constant. The way we'll write that constant is 1 over c. If that value for c is, if the absolute value, that value of c is bigger than 1, that's going to be a horizontal stretch by a factor of c. If its absolute value is less than 1, it's going to be a horizontal shrink by a factor of c. If it's equal to exactly 1, there's no change, right? There's no dilation happening. If it's vertical, the stretch or shrink is vertical, we're going to multiply the the y coordinate by a coefficient, or by a constant. We'll use the letter a to represent that constant. If the absolute value of that a is greater than 1, we have a vertical stretch by a factor of a. And I guess we should probably put absolute values around these. And if the absolute value of a is less than 1, it's going to be a vertical shrink by a factor of a. And if it's equal to exactly 1, there's no dilation, once again. So far, so good. Again, if I get going too fast, holler at me and I'll slow down. I know that sometimes it's a lot of writing. Drake, you said the other type was flips. That would be a reflection. And there's 2 types of reflections. We can reflect across the y axis. To do that, we need to negate the x coordinate. So basically, if that value for c is negative, then we have a reflection across the y-axis. And if, the value for c is positive, we have no reflection. The other type of reflection we'll talk about is reflecting across the x-axis. To do that, we're going to negate the y-coordinate. So if the a value is negative, we'll reflect across the x-axis. And if the a value is positive, there's no reflection. Okay, there's two more types of transformations. Does anybody remember? Yes, go ahead, Lily.
Rotation.
Okay, rotation is a third type. We're not going to talk about rotations in your high school math class because it's beyond the scope of what we're interested in doing. In particular, you need the trigonometry that we're doing this semester to do a rotation of a function. But that is a third type. And do you remember the fourth?
Like translation up down.
Yeah, translation. So there's two types of translations. Very good memories, guys. There's two types of translations. There's translations up and down, and there's translations left and right. So a horizontal translation, left and right, we're going to add or subtract a constant directly from the x coordinate. If h is positive, we're going to translate right h units. If that constant is negative, we're going to go left h units. And if it's 0, then it doesn't go left or right at all. The other option is a vertical. There we're going to add or subtract a constant directly from the y-coordinate. So if that constant's positive, it's going to be going up that many units. And if it's negative, we're going to be going down that many units. And if it's 0, it doesn't go up or down at all. Jack.
Can you scroll up for 1 second? Sorry. Thank you.
You're welcome. Yes, of course. Okay, so let's take a minute here and just look at some pictures about what I mean by these different types of transformations. So I just preloaded some stuff. I just want to turn some of it off here. So let's say our parent function is x. Yes, Sergio? Yes. So let's say our parent function is x squared, right? If I want to talk about a vertical translation, I'm going to either add or subtract something directly to that function. So like a +2 is going to translate it up 2 units. So there's my translated graph. Everybody okay there? If I wanted to translate it left or right, say I wanted to move it right 5 units, I'd subtract the 5 from the x-coordinate directly. So it's inside the squared, so that's going to shift it right 5 units. Yes, sir.
Where was this last year? Like, you could use this last year for transformations at the end, like every single chapter.
Yeah, it's the same information, man.
No, I know, but I'm saying that we were taught this last year, like the calculation.
Oh, did you have me second semester?
No.
Okay. Feel like we talked about it. Let's say I have 2 times x squared. There, that 2 is my a. Since that's bigger than 1, it should stretch it vertically, so it should get like taller and skinnier. So that's what we see there. As opposed to if I wanted to stretch it, or I'm sorry, shrink it shrink it vertically. Maybe I multiply by something less than 1. So that should make it like fatter and wider, which it does. If I'm going to do a horizontal stretch or shrink, I have to do it inside the x-coordinate. So maybe I'm going to do a horizontal stretch, right? My c value there is bigger than 2, or bigger than 1, excuse me. The c value is 2. So that should make it wider, which it does, right? And if I'm going to shrink it horizontally, I need to pick a c value that's less than 1. So I'm going to pick 0.5. Now, normally I wouldn't write this as 1 over 0.5. You'd write it as 2. Right? 1 over 0.5 is just 2. But just so you can see. So this should make it tall and skinny, which is what it does. We got a picture of kind of visually what these transformations are doing. So I just wanted to reinforce like visually what it is that we're writing down. So let's do some examples here. So that was basically the content. From here on out, it's just going to be some example problems. So let's say that our f of x is 3x squared. 3x squared plus 4x minus 1. And let's say we want to reflect this across the x-axis, the x-axis. Since we're talking about a reflection across the x-axis, I know that I need a negative value for a. And since there's no dilation being described here, I should pick -1 for the value for a. So my function should just be negative f of x. So when I apply that negative through my f of x, that's my resultant or transformed function. Right? No big deal. If I wanted to, say, reflect across the y, well, same idea. I know that the c this time is negative, and since no dilation is being described, I know I pick -1 for c. So g of x should be f of 1 over -1, which is just negative x, right? So that's going to be, have me plug in negative x for x into my f of x. And when I simplify it down, I got that. What if I wanted a vertical stretch by a factor of 3? So I'm not told that there's any reflection going on. So I know that the A should be positive. Because it's a factor of 3, we know that A is just going to be 3. So my transformation should just be 3 times f of x. So that'll be, 9x squared minus 12x plus 3. We're okay with that? Just 3 times our f of x. What if I want a horizontal shrink by a factor of 2? Again, since we're talking about horizontal stretches and shrinks, we're talking about the C. Since no reflection is mentioned, I know that C should be positive. So in this case, we're talking about a C of 2. So my transform function should be f of 1/2 x Oh my goodness. Sorry. Oh, Mr. Kulik. Should be 1/2. Yes.
When you're doing that, are you doing the transformation from the original function or the function you made from beforehand?
I'm doing it always back to the original f of x. So I'm not doing like successive transformations to f of x. I'm just starting back at f of x and say, oh, what if I wanted to do this to it? We'll do some successive transformations in a moment. But I just want to do like some of these one at a time to give you a feel for like what's going on. Sorry. Again, I'm getting 1/2 because it's a shrink. My apologies. I got going, I'm like, wait a minute, that's not right. So 2x times 2x is 4x squared times 3 is 12x squared minus 8x plus 1. Sorry about that. Let's see, E. What if we want to shift up 4 units? So since we're talking about shifting and going up, we know that's a vertical shift, so we're talking about a K. Since it's going up, K has to be positive, and since it's 4 units, it's going to be 4. So we have f of x plus 4. So that's just going to be 3x squared minus 4x plus 5. Right, just added 4 to the end of f of x. Oh. So what if we want to shift left 1 unit? Since we're talking about shifting horizontally, we're talking about the h. Since it's left that we're shifting, I know the h is going to be negative. And since it's going 1 unit, it's going to be -1. So that'll be f of x minus a -1, or just f of x plus 1. So when I plug that into my f of x, I get this. So I'm going to have to FOIL out x plus 1 and then distribute the 3 through. I'm going to do that all in my head. I hope that's okay with you guys. And when I combine like terms, then we get this. Oh my goodness. No, we don't. That should be -4. Woo! I caught it though, guys. Don't worry. Everybody makes mistakes, right? Okay, so let's look at some examples now where we do successive transformations. So we'll do one type of transformation followed by another one. So I'm going to make a new f of x. It's a little less algebraically difficult to deal with. And say we do we're going to shift up 3, then vertical stretch by a factor of 2. So if we're going up 3, that tells me that the k is 3. And if I'm doing a vertical stretch by 2, that tells me the a is 2. Everybody happy with that? So my first transformation is going to be the vertical shift up. So do f of x plus 3. My second transformation is going to be to take that previous result and multiply it by 2. Since we're applying 2 successive transformations to the same function. If we reverse the order, do you think we're going to get the same thing? If we stretch first and then shift? I don't know. Let's see. So just like before, this time g of x is going to be 2 times f of x. So that's 2x squared. And then h of x is going to be the previous transformation plus 3. So 2 of x squared plus 3. What do you notice here? Not the same. That's the takeaway. So that order in which we do the transformations matters. So let's talk about the order of transformations. So the first thing we're going to handle is the reflection across the y-axis. The next thing we're going to worry about is horizontal stretches and shrinks. Then we're going to worry about the reflection on the x-axis. And then the vertical stretch or shrink. And then the horizontal shift. And the last would be a vertical shift. So that's going to be kind of the order that we're going to use for our transformations. So if I give you the parent function, f of x equals x cubed, and I give you the transformed function, g of x equals 2 times the quantity x plus 1 cubed plus 4. And I ask you to describe the transformation that's being done in the proper order. This is how we'd kind of answer that kind of question. I would start by identifying the values for a, c, h, and k for my g of x equal to a times f of 1 minus c times x minus h plus k. In this case, what's my value for a? 2. Everybody good with that? What's my value for c? 1. Is everybody okay with that? What's my value for h? -1. Very good. Remember, it's always the opposite sign of what it appears. And the value for k is 4. Okay. So since c is positive, we have no reflection across the y-axis. And since c, the absolute value of c is equal to 1, we have no horizontal stretch or shrink. Since a is greater than 0, we have no reflection on the x-axis. And since the absolute value of a is bigger than 1, we do have a vertical stretch by a factor of 2. Since the h is less than 0, I know we're going to be shifting left 1 unit. I know it's left because it's negative. I know it's 1 unit because it's -1. And then lastly, since my k is positive, I'm going to shift up and then 4 units. It's up because the k is positive, and it's 4 units because it's 4. That should be pretty easy, right? Okay. Let's do a more challenging question. Let's say that we have f of x is equal to 2x squared minus 3. That's my parent function. And my resultant function is negative 6x plus 1 squared minus 1. And we're asked to describe the transformation in order that happened here. This is quite a bit more challenging, right? Because we can't just look at g of x and pull out the values for a, h, and k immediately, right? We're going to have to do a little bit more work here. So let me show you kind of the systematic way in which I would go about approaching a problem like this. So I'm going to think about this as 6 sequential transformations for the 6 transformations in order. So the first transformation in that order is reflecting across the y-axis. That occurs if the coefficient in front of the x is negative. If I look at my transformed function, that's certainly not the case, right? So my first transformation is just going to be, is just going to be the starting one, because I have no reflection across the y. Everybody's okay with that? The second transformation that I look for is a horizontal stretch or shrink. Again, to tell that, I need to look at the coefficient on the x. Since the coefficient on the x is just 1, again, I know that there's no horizontal stretch or shrink going on. Everybody's okay there? The next step, I'm going to look for a reflection across the x-axis. To do that, I need to make sure that my leading coefficient is an opposite sign, which it is. Everybody agree? So I'm going to do negative g2 of x. Everybody's good? Still doing okay? Jack? Or Jacob? Jacob, sorry.
But in order to use g of x and then 2f of x, or no, yeah. Why is the first one not the f of x?
Well, what we're doing is we're trying to show how this gets transformed to this. So the first thing I did was, okay, since there's no reflection, the first transformation from f to g, I didn't have to do anything because I didn't have to do it because there's no reflection going on. So just the first transformation did nothing. Is that okay?
Yeah.
Okay. Next thing we have to do is look for a vertical stretch or shrink. To do that, I'm again going to look at the leading coefficients. I notice that the leading coefficient of g is 3 times the leading coefficient of f if I ignore the sign. Does everybody agree with that? So g4 is just going to be 3 times g3. So that'll be negative 6x squared plus 9. Then I'm going to look for the horizontal shift. I see in here, inside attach the x, there is a horizontal shift going on. So to get that, I would have taken g4 and plugged in x plus 1. and then this was a shift left 1 unit. Because again, the h there would have been -1, right? Because we're adding, the h's are opposite. And then my last step is the vertical shift. So there I'm comparing the constant at the end. So right now it's +9. It needs to get to -1. So the k was -10. So it shifted down 10 units. And this is the piece where, looking at the two functions, it would be unlikely you would have come up with -10 for k without having kind of gone through this step-by-step process to build g from f one transformation at a time, right? Very likely you could have figured out the A, H, or A, C, H, and K from looking at the two. That wouldn't have been that difficult. To get that K, though, would have been quite a bit trickier. You know what I mean? Okay. I have one more example, and then I'm going to be done. Sound good? So let's say we have some function defined by this graph. And we want to graph the transformation g of x is equal to 2 times f of x plus 3 minus 1. So what I'm going to do is, the first thing I'll do is obtain the values for A, C, H, and K. In this problem, what's my A? 2. What's my C? 1. What's my H? -3. And my K? -1. Now, what I'm going to do is I'm going to use the following relationship. So to take a point in xy and turn it into a point in g of x, I'm going to do c times x plus h, and then a times y plus k. I can use this transformation always to go from parent to resultant. Amy?
So for the value of c, that just came from before the x, correct?
Correct.
Okay.
Yeah, it's the reciprocal of the number in front of the x.
And then it doesn't need to be negative. Just 3 would need to be negative.
Correct. Yeah, h is the only one that sign is not intuitive. Everything else, the sign is the same as whatever it is. Okay, so for our particular purposes, our transformation map is going to be x minus 3 to y minus 1. Everybody okay with that? I just plugged in my values for C, H, A, and K. And now I'm going to just take the points that are given to me on my graph and transform them using this. So negative 2 minus 3 is negative 5. 2 times 0 minus 1 is negative 1. 0 minus 3 is negative 3. 2 times negative 2 minus 1 is negative 5. Next one, 2 minus 3 is negative 1. 2 times 0 minus 1 is negative 1. 4 minus 3 is 1. And then 2 times 4 minus 1 is 7. So there's my points, or my transformed points. Is everybody good with that? Now I'm just going to go back to my graph, plot them, and connect them. And I'm done. So not too bad. So negative 5, 1 would be like over here. And then negative 3, 5, I don't know, like down here. And then negative 1, 1 is probably like there. And then 1, 7 is, I don't know, I'll put it like right there or something. Oops, that kept going. What do you guys think? Hopefully that's not too bad, right? Yeah. Okay.